Welcome to Math 105, Chapter 6.1, where we talk about sets and set operations. Now, in this section, or in this chapter, we're going to be working with a lot of like dice rolls and simulations. So if you do have a pair of dice, whether they are the same exact color or two different colors, or if you have both, that would be ideal. Now, if you don't have that, that's okay. Especially my online students, you can just follow the link in Canvas. It should say distinguishable and indistinguishable dice simulator. We're going to be using that in case you need some sort of a demonstration. For those who are not taking this online and instead face-to-face, we have dice in our classroom, so we're not even going to worry about it. So that being said, combinatorics is the theory of counting numbers of elements in a set. So what the heck are elements? What the heck is a set? Well, a set is a collection of items, and those items are called elements. Now, how we can say that in a mathematical way is just saying X, which is the element. So X is the item or the element found within A. So A being your set, X being the element or the item, I should say. And this little funky looking E is called your element. So this is how you can say X is found within A, the bigger set, or if it's not, you just put a slash through this funky looking E. Now, to get kind of an idea of what we're talking about, maybe you need a quick little doodad of a set. So take this citadel, and we can say either if it's people, you are an element of the citadel. You're attending the citadel. I am also an element of the citadel. I am teaching here at the citadel. You could also do it with buildings. Perhaps we got Thompson Hall. Maybe we have Capers. Maybe we got the cafeteria, right? All of these buildings could be the elements or the items that are found within the citadel. So it doesn't have to be people. It has to be something marginally countable that we're talking about. So that being said, we are going to be talking about different relations within these sets. One being a subset. This says B is an element of A when B does not equal A. This just means items in B are found in A, but not all A is found in B. So for example, if we have A is 1, 2, 3, 4, 5, and B is just 1 and 2, oops, 1 and 2, this B is located within A, so A kind of eats up B, is what that is really saying. However, we could also say B is a subset of A when B is equal to A. You could also phrase it differently. A is a subset of B, oops, when A is equal to B. This just means they are, all of their elements are found within each other. So A and B are equal sets. So perhaps A is equal to 1, 2, 3, and B is also equal to 1, 2, 3. So they are equivalent sets. Now, an empty set, you could say A is empty, right? It contains no elements. That symbol means no elements. For us, think about maybe an empty classroom. Or maybe a torn down building, right? Things like that. Now you can also have finite and infinite sets. Finite just means it terminates, it finishes after that bracket, whereas this ... means it's going to continue without bound. Now for a couple more quick examples, let's say we're rolling a pair of dice or choosing names from databases. Both of these are sets of outcomes. So perhaps if we're talking about the names in our classroom, right? We have student A, we have student B, student C, and so forth. And then we run out of students. Let's say I'm at max capacity, right? 20 or 25, right? So these individual students would be elements. And let's say we did small groups. Maybe we did a small group activity where I broke up group A to be student 1, 2, and 3. B would be student 4, 5, and 6, and so forth. We could keep breaking these up. And notice that they are not sharing elements, so they are not subsets of each other, unless perhaps I put student 1 in here as well, then there's some overlap to a degree. So if we did it one more time with rolling a pair of dice, right? The set of outcomes is the set of all things that can happen. So in our case, if we're talking about a dice, what are all the outcomes that are possible to us? Well, that would be 1, 2, 3, all the way up to 6, if we're talking about just a regular 6-sided dice. Which leads me to our first little activity. What is the difference between distinguishable and indistinguishable dice? So if you're in class, you would have been given the 2 different color dice, and then we'd swap and keep track of the rolls, right? So if you are an online person, okay, you're gonna go to, whether you have the dice already or you need a simulator, please go to the 2 links found in Canvas. Now what we're gonna do is we're gonna roll your dice 5 times. We're gonna start with 2 different colors. So 2 different colors, is that gonna be indistinguishable or distinguishable? Well, we're gonna be doing distinguishable. You can tell the difference using the 2 different colors. So we're gonna roll 5 times and keep track of which dice rolls what number. Then we're gonna repeat this experiment again using the same color dice, which are indistinguishable. And then I wanna figure out, well, what is the difference? So on my, there we go. So this this link is going to be the indistinguishable. Notice that they are the exact same. And this one is going to be distinguishable. So I'm gonna go ahead and give it a roll. I come up with a 5 and a 5. My yellow is a 5 and my white is a 5. White and yellow, 5 and a 5. Let's do it again. All right, we have 1 and 2, 6 and 1. 1 and 2, 6 and 1. All right, only 2 more times. My memory is not what it used to be. 1 and 4, 2 and 1, 1 and 4, 2 and 1. Okay, then I'm going to do white and white. Oops. Okay. Going to go to the other one. All right, I'm going to roll 6 and 5, 4 and 3, 6 and 5, 4 and 3. A couple more times, roll 5 and 3, 3 and 2, 5 and 3, 3 and 2, and one more. 1 and 6. Now, if you're doing this at home, make sure you're really shaking it up with both, like what you would do if you're playing an intense game, right? So taking a look at some of your outcomes and rolls, think about what the difference could be. Well, if we were to look at it, right? On this side, if I were to put this in like little, like not parentheses, but like a coordinate, oops, a little coordinate, right? 5 and 5, this standing for white and this standing for yellow, right? Let me write that a little bit better. Yellow, right? Which one was, white, we can clearly tell through the 5, and yellow, we can clearly tell also through the 5. Okay, let's do it again. 1 and 2. Again, this one is still my white one. This one is my yellow one. So which one through the 2? Well, the yellow one through the 2. Therefore, the white one through the yellow. And we can do this again and again. 1 and 4, 2 and 1. We can clearly see that this color is throwing either the 2, the 1, the 6, the 1, the 5. It's easy to keep track of. Same thing with your yellow. However, when I do it on the other side, right? White and white. We got 6 and 5, 4 and 3, 5 and 3, 3 and 2, 1 and 6. So when you put these in your hands, again, it's funny on a simulator because it doesn't give you that like aesthetic, right? You're putting it in your hand, you're shaking it up, and you throw it. And it does come out to have a 6 and a 5. And you do it again, but are we sure that this 4 is the same dice that threw this 6? Or that this 5 is the exact one that threw this 4 and this 6? Are we exactly sure that this 2 was rolled after this 1? Well, absolutely, because this one was the white dice. Even when you shake it up in your hand, you can follow along based on the color. This one, because they are identical, you cannot determine for certain unless you're breaking it up. My left hand is this, my right hand is this. Nobody does that, right? So our difference between the experiments is that you cannot determine which color through what through here, right? Or which dice through what on your indistinguishable. So that being said, right, that idea that you can definitely tell which dice through what versus this one, not so much. Can you find the set, the total number of options of distinguishable dice? And then again for indistinguishable. Now, if you're not quite following, let's see, hold on. 1, 2, 3, 4, 5, 6. Okay. So I'm going to leave that one blank. So let's say, wait, hold on. Why did I leave that one blank? 1, 2, 3, 4, 5, 6. Okay, yeah. So let's say, why did I leave that there? Is that what I wanted to do? Sorry, sometimes I have a hard time remembering what I was going to do, and I think that's what I wanted. So let's say I threw a 1 and a 1. Let's actually say this is, oh, that's probably why. This is distinguishable. So I'll have a red dice, 1, 2, 3, 4, 5, 6, and a green dice, also throwing 1, 2, 3, 4, 5, and a 6. Right? So my first roll, perhaps, I rolled a 1 and another 1, right? So can you figure out all of the different options? And then repeat with your indistinguishable. Now, there should be a difference based on the context of what we just came up with for your experiment, why these are so different. Doing it again with the distinguishable dice. Oh, sorry, indistinguishable. So we'll just do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Okay. So I'm hoping you're going to pause the video. I'm just going to fly through making this, and I might fill it out wrong first, and then we might go over why. All right, so like this. Okay. And I might fill this out wrong at the start. Okay. Let me do a little erasing. Okay. So I have 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3. Goes a lot faster in class because I can pause. So if you need to skip this part a little bit, please do so. All right, now I can do green. 1, 1, 1, 1, 1, 1, 2, 2, 2, 2. Okay, one more time. Okay. Paste. Again, I might fill this out wrong. In class, it's easy to set this up. 1, 1, 1, 1, 1, 1, 1. 2, 2, 2, 2, 2, 2. 1, 3, 3, 3, 3, 3, 3. 4, 4, 4, 4, 4. 5, 5. So I have it all filled out. Again, it might be correct, it might not be, okay? This is what typically students come up with. Now, one of these is actually correct. One of them is not right. So let's look at distinguishable. Again, our big takeaway was that distinguishable, we can tell which color through which option, right? So in this one, well, what color through the 3? Well, we can determine that the red one through the 3 and the white one, not the green one, through the 1, right? And we can do that for all of these. Let's see this one, right? 3 and 3. Red was 3, green was 3. Red was 5, green was 5. So we can certainly determine that all of these through which one through the right, or which color through each outcome. Whereas if we're looking at your indistinguishable, let's take a look at this first option, right? Well, which color through this 2? Well, yeah, it was this one, but okay. And this one through the one up here, but keep in mind, we're shaking it up in your hand. So let's look at this one, right? This one got thrown from this side and this 2 got thrown from the one up here. But again, we're shaking it up. How do I not know? How do I know for certainty that this one and this 2 are the same dice? Or this one and this 2 are the same dice? Right? Do we know for absolute certainty that these 2 are actually different outcomes? No. So if we don't know for certain, that's not an option. So let's take a look again right here, 3, 1. Other than knowing, okay, well, I have a 3 listed here and the 1 listed here, we don't know if it's the same outcome as this 1 and 3. I don't know for certain that I threw the 1 first over here, and then the next time it came up as a 3. We do not know that for certain. So by that logic, can we start to whittle down some of our options? Well, we can say that these ones are going to be repeated. They are all found within that first line. So then if we look down at the second, well, 2, 2, right? Okay, well, we shake up our hands. I get a 2 and I get a 2. Does that one repeat again at any point in time? No, right? But then keep looking. Down here, we got a 3, 2 and a 2, 3. Do we know that these are the exact same or different? We have no way of knowing. So it looks like a repeat. We're going to take it out. Same thing with the remaining. Keep doing that for the remainder of your options. 3, 3 is okay. 4, 3 is 3, 4. 5, 3 is 3, 5, and so forth. And we're going to keep going until we run out. So in this option, if I were to trace it, I should have something that looks like a diagonal. So distinguishable, we can have all of these different outcomes because we can see for certain which dice through which color, which dice through which number. And in total, we have 36 different options. This is called your sample space or your set of outcomes. Whereas your indistinguishable, if we have something that's already been repeated, we're going to get that out of there. So we're left with 21 different options. So total options or outcomes. So hopefully that makes sense. And we can move on. Set builder notation. It says let B equal 0, 2, 4, 6, and 8. Okay, so that is our set. If B is a set of all non-negative even integers less than 10, if we do not want to list the individual elements of B, instead we can use something called set builder notation. So this is just a nice way, or like a quicker way, to say all of that in words. So in the words, or in the English sentence, we might say B is a set of all n such that n is a non-negative integer less than 10. So instead, we can say B is equal to n, or the set of n, such that this line is meaning such that. Okay, so all n, this n, so that all of our n's preceding is a non-negative even integer less than 10. Now, while that might seem like a lot of words still, when you are actually studying math and you're like deep diving into it, we can actually break that sentence up even more. But since that's really not our problem right now, that's not what we're working on, we just want to figure out what this notation is at its very basic level. And just in case you're like, oh, it's the B is here. Is another way to say equals. The set of is just this little parentheses, not parentheses, they're called braces. So that's how you can go say and or read it in your homework. Now we're going to be talking about Venn diagrams in a second, and that is going to come in hand with what we had just talked about when it comes to being a subset. So a Venn diagram, how can we say X is an element of A? So if this circle represents A, then X is found within it. We've already kind of talked about that example from the Citadel, right? We go to the Citadel, we are an element of A, the Citadel. Whereas if we have that slash, we are not an element of A. Perhaps A is still the Citadel. We do not attend it. Perhaps we are at the College of Charleston. So in our next one, if A is equal to B, then A is a subset of B, and B is a subset of A. So if this is A here, B is going to be the exact same circle containing the exact same elements. Now, just think about this little equal sign. How would you read this or this, right? Less than or equal to, greater than or equal to. This is just that their subsets are equivalent sets. Whereas if we're talking about the opposite, notice that B and A are not equal, but B is a subset of A. B is found within A being this, B being inside of it. And our last vocab, mutually exclusive or disjoint events. We're going to have A on one end and B on the other, where they do not share. Do not share any elements. They have nothing in common. So that's kind of a visual idea of what we're working with. Now, with this in mind, we can actually have some like operations. There we go, set operations with it. So with these diagrams, now these operations, think about being like what you do like in your basic algebra, right? You can add, subtract, multiply, you name it, we can do it here, right? So if we're talking about the set of operations, we're going to be taking your new sets, or we're going to produce new sets from old sets. Now union, this first one being union, is going to look kind of like a U. Now, if you go to type the U button on WebAssign, it is not going to like it. It just is another word for or. You can type in either /union. Oh, actually, no, you guys can just type in union and it should pull up. Or when you click on it, you can go to the operation tool set and actually click this button. Now, the union, standing for or in our terms, says that we're going to take A. So all of A being this one right here. We're going to take all, oops, let me do that again. All of A. Let me shade that A in. We're going to take all of A or all of B. Put this one over there. So all of A, all of B, or both of them. So notice that there is some sort of an overlap between these values right here. Okay, what is going to happen is that we have now double counted. I don't know if you saw it, but when I went to shade, oops, when we went to shade, right, I shaded this region to start, which had a little bit of B in it, right? And then if I keep going, when I shade B, right, I'm now taking a chunk of A. Now, A had already been shaded. So what's going to happen is that we're going to trim the excess, right? We want to get rid of what has been double counted. It is overinflating our value. We're going to be showing an example of that in a moment. So this can be read as A or B or both. Now, the opposite of a union is your intersection. The intersection, where do they meet? In the middle. This is looks kind of like an N, right? This is standing for and. You can type in intersection or you can type in cap. The other one, I think sometimes you could write as cup as well for certain programs. So the intersection is exactly what it sounds like. It is where A and B meet in the middle. So it says A and B. So wherever they share, we're going to be using that value. Now there's one more that we're going to go discuss. It's called the complement. This is called not, right? So this actually can look like this little like prime or what is that little symbol? Sometimes in English, an apostrophe sign kind of looks like it. But the complement is not that value. So if this is A, and we're trying to find the complement of A, not A. Well, if this is A, if we had shaded A, we don't want this region. Instead, we want everything on the outside of this region. So everything here, oops, everything here I can do better with shading. Everything over here. Wow, I need to go back to first grade and learn how to color in between the lines. And everything here is considered not A. So let's see this in action. So if A is little a, B, C, and D, and big B is C, D, E, and F, then find the union and the intersection. Then find the complement. Well, if we're trying to find the intersect or the union, right? A or B. This says we're going to take all of A, okay? Taking all of A, B, C, D. We're going to take all of B, okay? C, D, E, F, and both, right? Well, take a look at your elements, right? If we have already included some values, right? I don't want to overinflate my number too much. I don't want to overcount some things, right? Over here, I've already taken B. Now, what has already been listed? Well, C and D have already been listed right here. So if they have already been listed, we only need to count them once. So that just means we can get rid of the overlap. We can get rid of the repeats. Cancel the overlap, the repeat. And I'm going to be saying that throughout our chapter 6, 7, and 8. Anytime you have a repeating value, if it's been overcounted, overinflated, we're going to subtract it out or just cancel it out. So if that's union, let's look at intersection. Intersection being A and B. So this one's pretty straightforward, right? Well, it just says take A and B overlap. Well, A and B, we just said overlapped with elements C and D. So then find the complement. So keep in mind A is A, B, C, and D, right? Well, if we're looking for not A, when we go to make your new set, none of these values are allowed to be in your new set, right? So what hasn't been accounted for? If none of these are allowed in, looking to be what is allowed in. Not C and D, so that means E and F. So not A means just anything that is not a part of A. Now I should have, and I should have made a note next time, is that set is the all of your options. So listing out all of your options, we actually kind of already did that in one of yours. It's just A, B, C, D, E, and F. So all of our different possible outcomes. We could have had another set as well thrown in the mix, which we're going to be seeing in example 2. So with that in mind, see if you can try example 2 on your own. It says nobelbooks.com maintains a database of customers, and the type of books they have purchased in the company's database is a set of customers. S is equal to Marilyn, Jackie, Billy, Danny, Renee, Robert, Kim, and Laurie. The customers who have purchased history yields a subset A. The customers who have purchased mysteries yields a subset B. And those who have registered with the site but not used their first-time customer discount is C. So they're going to tell us who fits the mold. So with that in mind, can you guys put this into a Venn diagram? Well, if this one is history, we'll label this one as A, right? Well, we have history here. We have, let's see, green. We have mystery. We have this reddish color or orangey as registered. No discount, right? So if we're putting it all together, those who are found in history are Marilyn, Renee, Robert, and Billy. But notice, before I put down Billy, when I go to look at mysteries, which I'll put right over here, Billy is already found in mysteries. And he is also found in A, history. So instead of just putting him only in A, we're going to put him in that overlapping section. So we'll put him there. Everybody else, let's see, Jackie, Danny can go in there. And then Kim is the only one who has not registered. Now, is there anybody that we have not accounted for? Looking back at S, your set, everybody who has come into the store or database, one of them is not listed. That person would be Laurie. So she just wasn't a part of this, this book survey. She's clearly used her first time customer discount, so she doesn't fit any of these, but she still was included. So once we have your bigger picture, can we find the set of customers who have purchased either histories or mysteries, those who have purchased both histories and mysteries, and those who have not purchased history? Then find the subset of customers who have purchased histories but have not used their first time customer discount. So definitely pause the video and see what you can do. So if we're talking about your A, your history, and your mysteries, we said we got Billy here, we got Marilyn, Renee, Robert, we got Jackie, and Danny. So the subset of customers who have either purchased history or mystery would actually be all of these. Now notice that Billy, because we put him instead of in both, we actually put him in once in the middle. We now do not have to double count him. So A or B is Maryland, Renee, Robert, Billy, Jackie, and Danny. Now, the subset of customers who have purchased both history and mysteries would in fact be only Billy. Okay. The customers who have not purchased histories. So in history, we have Marilyn, Renee, Robert, and Billy. So we do not want these individuals, so we're going to cancel them out. And instead, who would be left over? Well, we would have Jackie, Danny, Kim, and Laurie. Those are people who did not purchase histories. And the last one, it says the subset of customers who have purchased history but have not used their first time customer discount. So this means they are found in history, but have not. But have not is just another way to say and. So if you see the word but or however, it's just a fancy way to say and not see their first time discount. So here we're looking for anybody who has purchased history. Okay, anybody who purchased history, but not, none of these guys, their first time customer discount. We're looking for an overlap between the values. Now, since there is no overlap, it is empty. It's an empty set. No one has purchased history and not used their discount, right? So there's an empty set. Now, the last thing we're going to be doing is your Cartesian product. So we've learned how to kind of add values together. The canceling out of people, because Billy did not go in both, we've actually just placed him in one, or the idea that we have canceled these out is just a means of subtraction. So now we actually have multiplication, product, multiplying. Cartesian product is a type of set operation. Where two sets A and B is the set of all ordered pairs, A and B, with little a being an element of the big A, and little b is an element of the big B. So these are your items. And A and B, big B, are your sets. So, for example, if A is A and B is 1, 2, 3, then A times B. So each element of A has to be paired with each element of B. Thinking about what you perhaps did back in an algebra class where we tried to FOIL, right? Distributing is exactly what we're going to be doing. So A1, A2, A3. Every single element of this A is found and paired with this B. Doing it again, we get B1, B2, B3, and then we're done. So A, and then we get B, 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 and one more time. I like to make things look nice and pretty. 1, 1, 2, 2, and get that one. 3, 3. Now this is nice because what we're going to be doing in chapter 6, what are these called? We're going to be working with a pivot table, so kind of like a matrix, where then you can actually visually see why this might be appealing. So if we were to do the next one where it says A is red and blue and B is Ford and Toyota, then we can actually build them together. So your first element is a red Ford. Your second is a blue Ford. And then again, red Toyota and a blue Toyota. So it might seem pretty silly and basic right now, but you're going to be seeing the usefulness when we do go with a pivot table. All right, I believe that is it for now. Yes, that is. All right, see you later.